What chapter are we going to talk about today, gang? What is it? Begins with E. Energy. How many people feel energy? How many people wish they had more? We'll be talking about such thing now. But before we talk about energy, I want to talk about something that was somewhat related. We talked before about the idea of momentum. Remember momentum? Momentum is inertia in motion. And how do you get something moving if it's not moving? How do you change the momentum of something? You push on it, and you provide what's called an impulse. Impulse, right? Impulse is not only force. It's not how hard you push only that will tell you how much momentum change you'll get. It's how long you push. And we talked about how long in terms of time, didn't we? We said force multiplied by time would be numerically equal to. You multiply the force that you exert on something, huh? Multiply by the time that you exert on something, you'll get a numerical quantity. And that quantity is exactly equal to, not the momentum, but the change in momentum that you produce by pushing, huh? And so we talked about this, you know, and we called this idea here, how hard you push multiplied by the duration in which pushing takes place. We had a name for that. See if your neighbor remembers the name. E. Don't be an imp now, come on, come on. What is it, gang? Impulse. Yeah, don't be afraid to be a little verbal, all right? And so we said impulse is a change in the quantity, inertia in motion, moving inertia. We call that what? That oomph, what do we call it? Begin with an M. Momentum. Okay, don't be shy. And that's what we talked about, right? And we said for big changes in momentum, you'll have what kind of impulses? Begin with B. Big. For small changes in momentum, you'll have what kind of impulse? Begin with S. Small, all right? Now what happens to the change in momentum when bouncing occurs? Larger or the same as if bouncing does not occur? Begin with a L. Larger. And we can show that with this device here. Here's a dart. It's like a dart, and I have a sharp nail in there. And what I'm going to do is I'm going to lift the dart up, and I'm going to allow it to swing against that block. It's going to make a collision. Watch this. The block did not tip. I'll try it again. The block did not tip. This time I'm going to remove the point. And now I have just rubber here. This time when I swing it, it's going to bounce. And when it bounces, more impact or less? More. Wow, hands down. No contest. I don't even have to lift it even as high. I can even lift it this high, watch. Yay. So bouncing. More change in momentum when it bounces. When this comes down and stops, boom, there's a certain change. But when it hits, stops, and then it comes back out again, then what? More change or less? More change. More change in momentum means what kind of impulse? Greater impulse. And you saw that. And it's the impulse that knocked the block over. Hey, huh? Physics. We're not going to talk about impulse and momentum today. We're going to talk about a related idea. How hard you push to get something going is one thing, but how long you push is also important. So far we talked about how long in terms of time. How long in terms of what your watch reads. We can talk about how long in terms of distance, that's right. And when we do that, force times distance, it turns out we'll get a change in some other quantity. And that other quantity is not momentum, it begins with the E, energy, okay? And this is what we're going to talk about today. Force times distance will produce a change in energy. What is energy? Energy is that numerical quantity which appears in many, many forms. Like mechanical energy. We'll talk about mechanical energy today, really. Energy of position, potential energy. Energy of motion, motion energy. We don't say motion energy. We use a Greek word for motion. Begins with a K. Check your neighbor, see if your neighbor's on. What's motion energy with K? Kinetic. Yeah, kinetic energy, okay? And then we could talk about, later on, we could talk about heat energy. Sound energy. Can anyone think of any other kinds of energy? How many say, no, that's probably it. There's probably no more. Come on, gang. Some more. Light energy.
Potential.
Good. Radiant energy. Radiant, from radium, things like that, huh? Good. Thermal energy. Good. Nuclear energy. And it turns out energy of being. It turns out everything has this quantity called energy. And that's given by Einstein's celebrated equation. Later in the course, we'll talk more about this. The idea that energy and mass are two sides, gang, of the same coin. You guys get mass, right? You know what your mass is? Squashed up energy. You are all bits of energy, all squashed up. And the more massive you are, the more energy you have. And sometimes you can convert from the inertia kind to the radiant kind. And that's what happens in the sun and the stars. And that's the energy of fusion. And we'll talk about that too. But today we're only going to talk about the simplest kind of energy, mechanical energy, and its related idea, work. Because this, force times distance, we don't call that impulse, gang. No, force times time is impulse. We call force times distance another word. See if your neighbor doesn't know what it is. Who came unprepared? Doesn't know. What is it, gang? All together. Work. All right, work. We call that work. Okay, work equals a change in, and I'll just put E for energy, all right? If I'm lifting something up, if I lift this block up, I do work on the block when I lift it because I'm exerting a force through some distance. Okay? And the higher I lift it, the more work I do. The more work I do, the more what it has. It begins with the E. Energy. Okay? If I elevate way, way, way up, it's got a lot of energy. And we call that energy energy of position. And that energy of position, you could put the work in today and you could use it tomorrow. So you can store it. It can be there for your potential use. So that being the case, gang, we got a name for energy of position. Begin with PE. What is it? Potential energy. Potential energy is energy of position. We talked before about a slingshot. When you pull a slingshot back further, okay, boom, the projectile's going to go faster. And we said it's going to go faster, it got more momentum. Today we're going to say, yeah, it's got more momentum, but if it has momentum, it also has something else. It begins with an E. Try it. All right, ends with Y. Energy, okay? But now it's energy of motion. And we call kinetic, energy of motion what, gang? Yeah, so I can go like this and pull it with position. More position, more position, more energy, whip, boom, more what? More kinetic energy, that's right. How about cannons? How about you get a cannon like this? It's that long. Okay, and you fire a cannonball. Out comes the cannonball, huh? Let's suppose you have another cannon. Same kind of cannon, only larger. Now, you fire the same kind of cannonball, the same amount of powder, out it goes. In which case will the cannonball go further? How many say the longer one? Show of hands. E. How many say the longer one because there's more impulse on it? Show of hands. How many say, wait a minute, impulse was the other day. I don't know about today. Come on, impulse. What is impulse, gang? It's the force and the time during which it acts. But couldn't we also say, hey, it's going to go further because there's more energy given to it? How many see that? Even if the force is the same. Because over here, I hit with a certain force, here a certain force. But here the force acts over this distance. Here the force acts over this distance. Which is bigger, this quantity or this quantity? This quantity. So you're doing more work on the cannonball, so it's going to leave with more kinetic energy. And we can kind of see if something got a lot of kinetic energy, it got a lot of momentum. If it got a little kinetic energy, it got a little momentum. They're related. They're related. That means it can be confusing sometimes. We're not going to push that to death, though. Just want you to know that when you do work on something, you can change the energy that it has. I can kind of show you that with this bowling ball over here. Here's a bowling ball suspended from the ceiling. And what I'm going to do is I'm going to do work on this bowling ball and increase its potential energy. Because what I'm going to do is I'm going to pull the bowling ball back. Now it's going to take a force to do that. This little device here will show the force that I apply. And we can look at this kind of close up, and we can see that as I pull it more and more, the force gets more, greater, greater, greater. Notice the force is varying with the angle. It gets very complicated to multiply the force times the distance because the force keeps changing with the distance. So to calculate that, you need a kind of mathematics that we're not into right now, and it's called calculus. But it turns out when I do that and I pull with an increasing force higher, 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 I'll get a particular number here. But you know what? I've raised it this high off the ground. If I simply pick it up straight up, it takes more force. But I go a smaller distance. And guess what that greater force times a smaller distance is compared to the variable force times a long distance? Take one guess what the energy is at the end both ways.
Same.
Take a guess. Begins with a SS. Now take a guess. How many sitting next to someone? Oh, well, check the neighbor. Check the neighbor. What is it, gang? Same. That's right. That's right. I'll show you another nice thing with this pendulum. This pendulum illustrates one of the most important ideas in physics. What I'm going to do is I'm going to hold this against my teeth, and I'm going to let it go, okay? And you watch and see what happens. I didn't flinch, man. Shall I do it again? I'll close my eyes. Oh, no, I really did have my eyes closed, okay? You know what, gang? What's this illustrating? How many say, oh, it's probably not illustrating anything. It's just a bowling ball going back and come on, you guys. This illustrates energy conservation. The idea that you don't create or you don't destroy energy. You just slish-slosh it from one form to another. When I lifted this up, it had energy of what? Begin with P. Position, right? And when I let it go, it turns into energy of motion, kinetic, right? And so the position, motion, position, motion, position. But here's the idea. When I started, I did work and lifted it to a certain amount. It's got a certain amount of energy, call it 1,000 units. When I let it go, whoops. Well, I did a little work on the wall, okay? But the idea is it will never come up higher. If it came up higher, it would have more than 1,000 units. And we have a little dictum in physics. No can be. Or we've never seen such a thing. Never has anyone recorded and verified the idea that something could put out more energy than was put into it. We call that idea the conservation of energy. The pendulum at this level is lifted and has a certain potential energy at this point. A potential energy with respect to, say, this level. That's how much potential energy. Maybe it's 1,000 units. Let's call it 1,000. Those units, by the way, would be called joules, Newton meter. We're not going to get too much into that, too deeply into that. But say 1,000 units of energy here. Now it goes into, whoom, no more potential energy. It's all what kind of energy, gang? Kinetic. Some people know the value of the kinetic energy there, and some people don't. See if you're sitting next to someone who do. How many say it's 1,000? How many don't really know? How many? I don't know. I haven't paid attention, man. I don't know what it is. Show of hands. Okay. It's 1,000, yeah, 1,000 joules. And when it goes to the other side, what will it be? 1,000 or not quite? It turns out not quite. Boom, energy's been destroyed. Yes or no? Has to begin with an N. Account for the energy then. It turns out when you swing it, it never quite comes back to where it was. Do you know why? It's transferring the energy somewhere else. Guess where? How's the temperature feel today, gang? Relatively cool? How many say, that's strange, it seems to be warming up? Okay, a little exaggeration, but it is. That thing's banging into the air. And when it bangs into the air, boom, what happened to the air molecule? Move a little faster. And we'll learn later on that kinetic energy of air molecules, honey, we're talking about temperature. And so what will happen is the energy will go from that to the energy of the molecules in the room. It dissipates in the form of heat. See? But you always have it there. It always adds up, and that's kind of nice. All the physics experiments you do, you always find out the energy score remains the same. And sometimes when it doesn't seem to, you discover things that maybe you didn't know about before. It's marvelous, a marvelous principle of physics. Conservation of energy. To calculate the energy of any system. Maybe it's a galaxy about to explode. Calculate the total energy. Let that galaxy do, no matter what it wants to do, spin around, explode, I don't care what. Some big event. Then draw a dotted line around it, calculate the energy in there again, and what do you got? Guess what? Same darn number. It might be different forms now, maybe more light than before. But the energy just transforms from one form to another, and that's kind of neat. Let's suppose we have the case of a person up at the top of a flagpole. And they're up at the top of that flagpole, and they're going to dive into a little bucket of water. We used to do this in circuses, okay? And here's a dude up here. He's going to jump. And let's suppose up at the top there, he has 10,000 units of energy. That's his potential energy, isn't it? He's at rest. So being at rest, what would his kinetic energy be? Zero. We'll just say 0. And here, right into the bucket. When he gets down to the bottom of the bucket, the potential energy is what? 0. Because we took this with respect to the ground. So down here it's got a potential energy of 0. I know you're sitting next to someone knows what the kinetic energy of splat is. I know you do the, just double check to be sure. What's the value of the kinetic energy here? How much kinetic energy? How many people don't say 10,000? Okay, come on, you guys. There's going to be 10,000. 10,000 units. Hey, when the dude gets halfway down, the potential energy is only half. 5,000. There are people can calculate what the kinetic energy must be. See if you're sitting next to one. What's it going to be, gang? 5,000. Let's suppose when he gets 3/4 of the way down, his potential energy over here is now only what? It's 1/4 of this, 1/4 of that. Looks like 2,500. Will the kinetic energy be more or less? You know it's going to be more. Picking up, huh? And what will the kinetic energy be at the 1/4 up mark? E, huh? 75. Such that what? Do you see the rule here? Here, 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 anywhere. Going to have the same energy. And when he finally comes down here, the kinetic energy goes to 0. Boom. Calculate the heat of the bucket and the heat of his remains. And what do you got? Then you've got 10,000 units of heat energy. And that dissipates, dissipates, dissipates. But it's always there. Energy score stays the same. I'll show you something kind of neat. Here, I've got a piece of metal. I'm going to weigh it. The hunk of metal weighs a little bit more than 10 newtons. Just about 10.5 newtons. See that? Okay, 10.5 newtons. Now what I'm going to do is I'm going to hold it with 2 scales. And you guys tell me what's the reading going to be in each scale. Now this is old stuff. 1 scale there, 1 scale here. Wish I had one more hand. It should be half, gang. Is it half? Let me take this one off. And at an angle, it gets wild. Information overload today. So we'll only talk about straight up and down. Okay? My klutziness is showing. There we go. Half? So I can hold it up with half as much force when this supplies the other side. Huh? Is that right? Okay. Now I'm going to do work on this and lift it. Okay? Let's suppose, first of all, I do work and I lift it like this. I want to lift it. Let's suppose I want to lift that up to the 20 centimeter mark. Okay, right to here. Okay, watch this. How high did I move my hand? I moved the bottom of this up 20 centimeters. How far did my hand move? More, less, or the same? Did you see it's the same? If you take that reading, which is about 10 and a half, and multiply it by the 20 centimeters, you'll get a number. Okay? That's a number. That's the amount of work I'm doing when I lift it up. Okay? And it's going to take that amount of work to lift it up 20 centimeters. Let me put that on the board. The work I'm going to do as force times distance is going to be, let's round it off to 10, okay? 10 newtons. And the distance, I raised it where it was 20 centimeters, or 2/10 of a meter. 2/10 of a meter. And that's going to be equal to 2 Newton meter, and we call that a joule. 2 joules of work to lift it up 20 centimeters. I'm going to lift it up 20 centimeters again. But I don't like having to pull so hard. I don't want to pull with 10 newtons. I'm getting tired. I'd like to pull with about 5 newtons. How could I do that? I could tie this onto here. We have to wonder if the ancients who constructed the pyramids knew about so simple an idea as we're talking about today. Because now I can lift it, as you've seen, with half the force. Half the force. Now I'm going to lift this up 20 centimeters, and you watch how far my hand moves. Where's the 20 centimeter mark? Right here. How far did my hand move? More, the same, or less? Much more. Can you see twice as much? I moved my hand through 4/10 of a meter. But the force I exerted was only 5 newtons. But I had to exert it through twice as much. And what's the result, gang? 2 joules. This is like a machine. Some people think that a machine can change the amount of energy. Those people are wrong. A machine can't put out any more energy, any more work than put into it. What a machine can do is change the force that's required to do that work. So whether it's a pulley system or whether it's a lever, the work you put in is the work you get out. And you could hold the lever at different positions, and you could get different forces to do the same work. But watch out, gang. No machine can put out more energy than is put into it. Okay? What can it change? See if your neighbor knows. We can kind of see the answer to that when we look at the equation for work. Work is what? Force times distance. Since the work input, work output is the same, what you can do is you can slish-slosh back and forth between whether you're increasing force or increasing distance. Consider a huge truck with a flat tire. And that truck got to be lifted so the tire can be taken off. Can you imagine the ancients, back when the pyramids were being built, seeing a little girl using a bumper jack to lift the Mack truck? A little kid. And they'd come by and they'd see the kid go, and they'd see the truck come up in the air. Say, my gosh, kid, how did you lift that truck? And she said, well, I had to just do some work on the jack, and the work on the jack did work on the truck, and the work on the truck, same as the work on the jack, no big deal. This is 20th century stuff. He says, but I'm not 20th century yet. Could you explain that to me? And the little girl would say this, well, look at this. When I push down, she says, I have to push only a little force compared to the force of the truck. But when I push down, look how far I got to go. She said, multiply my push times the distance I push. You get a number, right? And all the people say, yeah, you got a number. Say, now multiply the force on the other side by how high it go. And you get a number, right? And guess how big the numbers are compared to each other, gang? Same, same. What if she went like this? Click, click. And the truck went click, click. Woo-hoo-hoo. Honey, that's magic. That's not physics. You hear me? Okay? But isn't that neat? That it always turns out to be just the force down times the distance equals the force times the distance. And we kind of show that like this. The force she might push would be like that. And the force she lifts might be like that. But the distance she pushes is like that. And the distance this rises is like that. And these would be the same. Not quite the same. Some of the energy goes into working and heating up the jack a little bit. So this number is always a little bit smaller. And how much smaller we get into the idea of efficiency. Won't talk about that today. But with ideal efficiency, this can never be bigger than this. So you're walking down the street and you see some dude pulling on a pulley system, and you see him single-handedly lifting a piano, and a piano is going up in the air. A piano that a human being could never lift. One of the grand piano type jobs, okay? And here we go, chung, 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 and that piano's going up in the air. How can be such a thing? Well, first of all, if the pulley system means that the piano is being held by 10 ropes, then the rope tension would be the same in all 10, barring friction. Then his free end, he's pulling one of those tensions, the same as those. So he's got 1/10 the weight of the piano on every rope, the one he's pulling. So if the piano weighs 1,000, he pulls 1/10 of 1,000. What's that? 100. If he can pull 100, up it goes. But furthermore, you multiply how many meters of rope go through his hands by the force he pulls, you get a number, yeah? Now, multiply the weight of the piano, humongous, huh? Times the amount of meters it goes up, smaller number, yeah? Multiply those two together. What's the biggest that number can be? Yay, same. Ain't that neat? It works. It works. Energy. I remember years ago I used to hear people talk about the so-called conspiracy of the oil companies. That their cars, automobiles, with little gadgets, usually involving magnets, attached to the carburetors of the cars, would allow cars to go fantastic distances. But the oil companies have bought up the patents, and they're withholding it from the public, so the public will have to guzzle down more oil, make more money for the companies. See the idea? That maybe, I was told one time, for example, that with these devices, one could put a couple of liters of gasoline in your car and drive from Boston, Massachusetts to San Francisco in a couple of liters. But the oil companies won't let you do it, so you have to burn a couple of barrels or something like that. Well, how about that, gang? Are there any rules that govern this sort of thing? Answer begin with a Y. Try it. Ends with a P. Try it. Yep, there is. And that's the energy conservation rule. And let's talk about that right here. Okay? We're going to push the car across country. It's going to take energy to do that. It's going to take energy to do work on the car. And that work is the force times the distance that we're pushing the car. Now, what's the force that keeps a car going, even in a straight road? What's the car? What's the force? It's the force against friction. And for a very streamlined car, that force can be something like 1,000 newtons. 1,000 newtons at highway speed. So let's see what happens. What's the energy over here? That's the energy given to us by the gasoline. And that's a certain amount. It turns out gasoline has an energy content of about 40 million joules per liter. 40 million. Now, this is what the energy thing means. If you have 40 million units of energy to spend, that's the energy content in your gasoline. What we're saying is, these two numbers multiplied together can't be bigger than that. Because that's what you got to spend in your gas tank. I don't care what kind of gadget you got. That's it. Now, how are you going to do it? You're going to push your car through some distance. Let's see how far you can push it. How far can you push it? Well, if you're pushing it uphill, it's going to take more force, so this will be smaller. Pushing it downhill, maybe gravity will do it for you. You don't even need anything, okay? But along a level road, you got to push against the air drag. Isn't that true? The faster you go, the more air drag. And let's take an average unit of 1,000 newtons. 1,000 newtons for our force. And now we want to calculate. Can we calculate, gang, at our seats, huh? Pencil and paper? What's the distance that the car could go with 1,000 units of force pushing it along? How many kilometers will the car go on that 1 liter? Calculate such thing now. Am I doing it right, gang? Am I doing it right? If this times this equals that, then this equals that divided by this. Is that right? Is that the algebra? We can do that? Look at the zeros, honey. Now, anyone have a calculator? How about without a calculator? We can do? Huh? 1 goes into 40,000 how many times? 40,000. So this car is going to go 40,000 meters. And it turns out, if we express force in newtons, distance in meters, and energy in joules, the units will match. So we have no conversions to make. So this turns out to be 40,000 meters. We don't say 40,000 meters. We say 40 kilometers. So it turns out to be 40 kilometers. You know what this means, gang? In a car that is 100% efficient, you can't have that. Make believe you can. 100% efficient. That means all the energy of the gasoline goes into moving the car. None goes into the heat, none goes into the sound, none goes into the friction, huh? All into the car. That's the upper limit. If you have to push with 1,000 newtons, which is reasonable, then the greatest distance you can possibly get, nature's ultimate, is 40 kilometers. So this car will give you 40 kilometers per liter. And there's only one way you can get more. How's that? Well, what is that? This is, huh? How can you get more distance?
You go outside the car and you push on it yourself.
By changing the force. That's right. If you can decrease the force, then you can increase the distance. Do you see that? And how do we decrease the force with cars? We make them streamlined, so they cut through less air drag as they move. Isn't that nice? See? And usually you're going to get about 25% efficiency, which means you'll get 25% of this, okay, which means you usually get about 10 kilometers per liter. See? Yeah. So what you're trying to do is to increase the efficiency. But this is in the upper limit. See? Now, most people don't realize this. People don't know there's an upper limit, that nature's limit. And they think that little gadgets or something can somehow beat this. And many of the devices that are submitted to the patent office flout this altogether. And the first thing the patent types do with some particular machine, they say, wait a minute, is it going to violate the conservation of energy? If it does, we don't want to look at it. And the reason is, the patent people have looked through thousands and thousands and thousands of schemes, maybe hundreds and hundreds of schemes, which all seem to give you out more energy than before, and they find out where the little flaw is. So at this point, they just say, look, if it violates energy conservation, come on, it's another wacko. Because nothing has so far shown that you can get more out than you put in. So there are rules to the universe, and that's one, energy conservation. You can change from one form to another, but you can't get more than you started with. No free lunch, gang. And with most machines, you don't even break even, because some of that energy goes into overcoming friction, turns into heat. So why do you eat your cornflakes in the morning, gang? You eat your cornflakes in the morning because what do? Those things are being torn apart in your stomach. And when they're torn apart, the bonds, that energy becomes part of guess who? And you use that to go about your day. And what happens? You stop eating. How long can you keep running your car without putting gasoline in? How long can you keep running your body engine without putting food in? So the conservation of energy, hey, biology, we're right underneath. Here's a neat little device here. It's a generator. Consists of magnets, these magnets. And inside here I have a coil of wire. And I'm going to turn that coil of wire. And the coil of wire is going to turn inside the region called the magnetic field. And when it does that, it's going to induce electricity. And when I do that, I can light the lamp. How that happens, we'll talk about later in the course. But for now, we can look at this in terms of energy. That light that you saw glowing, that's a form of energy. What was the source of that energy? It was the cornflakes I ate this morning. Because it takes work, I have to work on this to turn it. See that? And if I want to make it brighter, I got to work more. Isn't that neat? Okay. Later we'll learn that if someone could keep turning this thing, we could generate electricity to light up cities. And sure enough, we do. And we have devices like this, and we put a waterfall over here and turn it, use the energy of the waterfall, potential, kinetic, boom, rotational, boom, mechanical, off it goes as light, huh? Do that. Or we could put a steam turbine here, direct some expanding steam against a turbine, against a paddle wheel, and turn it. And so our civilization really rests on devices like this. But there's got to be some energy input to be transformed over here. Now here's a neat little thing. When I turn this, and I unscrew the lamp, it becomes easier to turn. Easier to turn. Why? Well, when it's unhooked, there's no energy going off. And so all I'm turning against now is the friction. But when it's hooked up, I'm pushing against the friction plus the electricity. So I can show you that. Can I have a volunteer? Could you come up here, please? What I'm going to do, could you stand over here? And what I want you to do is, I'm not going to look. I'm going to look over here, okay? And I want you to unscrew that. And I'll tell you when it's unscrewed because I'll feel the difference over here. So let's tighten it up now. Okay, I'm going to do it. Okay. Ah, you just unscrewed. Screw it again. Ah, now it's on. Ah, off. How do I know? I'm looking at the mirror right up here. No. But you see that? You try it. You try it. Can you feel it easier? Just do it. Go ahead. See if it gets harder. Okay, keep a nice steady cadence. Yeah. Oh, yeah. No, never mind the mirror. Okay, here we go. Go ahead. Go ahead. Notice. How about now? Harder. Harder. Okay.
Easier. It's gone.
Is that nice? Okay. Okay. The handle knows whether the lamp is on. Ooh. How about that? What's going on there, gang? Even why that happens, the mechanics of why that happens, we're going to get up to when we get up to electricity and magnetism. Delicious stuff, okay? But we see that energy conserved. The energy I put in, the energy come out, okay? Like that. Much easier to turn it. Try it after class yourself. It takes energy to light the lamp. That being the case, let me ask you a question. You get your car. You want to find out what your gas mileage is because you want to compare it with your friends' cars. You all got a contest. This friend is bragging about getting so much mileage, You want to test yours too. So you're driving your car and you're driving along the highway. You're looking at the speedometer. You see how miles you go. Tank it up later on. See how much gas. Divide one to the other. You see how many miles per gallon you got. How many kilometers per liter. Yeah? And you're doing that, and you're driving along, and as you're doing that, someone reaches over and turns on the radio and pulls out the light switch and pushes in the cigarette lighter. And you say, would you cut that out? You're screwing up my gas mileage. True or false? Check your neighbor. What's the answer, gang? Begin with F? End with alt? Or does it begin with T, ends with ru? Which one? How many say true? How many say, hey, when you're driving at nighttime, if you want to save on gas, what should you do? Put your lights off. People say, how come you're driving with no lights? I'm trying to save gas. True or false? True. No, true. That's right. So I want you guys to all learn something from this course. I don't want you driving at night with your lights on. Drive with your lights off, right? No, maybe it's worth to burn a little more gasoline to keep from crunching up, huh? But nevertheless, you are burning more gasoline when you put your lights on. See if your friends know that. Now, a lot or a little? Answer begins with an L. Probably a little, okay? Probably a little. But you really are. There's no free lunch. How about your aircon in your car, your air conditioner? When you put the aircon on, does it burn more gas? Something, what, an aircon? Just hooked to there's a belt from that spins that thing. That's just hooked down to the drive shaft anyway. The old drive shaft turning, the hook on. I mean, it doesn't know the difference. It doesn't know the difference. Did this know the difference when this was on? It knows the difference. It's got to push, it's got to do work. You're going to burn a lot more gas with your air conditioner on. You know why? Especially on a hot, hot day. Because now you're having to put out more energy to get to air condition the car. More energy. How we do that, we're going to be talking about later. Okay? We'll talk about that too. Ain't that nice? A whole lot of ideas we can talk about, because all these ideas begin with F. What are they? Physics. That's right. Yeah. Let's talk a little bit about kinetic energy. I haven't given you the relationship for kinetic energy yet. Let me give it to you. It's a little tricky. I'm not going to derive it. It's derived in the footnote in your text. I'll just state it without proof. It's half the mass multiplied by the speed squared. Remember, momentum was just mass times speed. Simple, simple. This somewhat more complex, because it's half the mass times the speed squared. The square of the speed tells you that, wow, it really depends on speed, because it's speed multiplied by speed. So it's very, very speed dependent. When we talked about firing the rifle before, the momentum of the bullet equal the momentum of the rifle coming back. So momentum, momentum, same. Impulse, impulse, same. But that was kind of bothersome to some people, because this has got something more than this. And you know what it has more of? Energy, okay? Because the had a bigger speed, but now with energy it's squared. Whoo! So the bullet going out might have the same momentum as the gun coming back. But honey, most of the energy is in the bullet, not the gun, because we're squaring that greater speed. You square the speed, the results of, give you an example. You're driving down the road in your car, and you're going 30 kilometers per hour. And you step on the brakes, you screech to a stop. You're going to change your kinetic energy. You're going to change it from the kinetic energy you have at 30 kilometers per hour down to 0. What's it take to change that kinetic energy, gang? It takes work. And that work is what? What kind of work stops your car? We can let the equation guide our thinking. It's a force and it's a distance. Distance is the distance your car skids, yeah? And the force must be the friction force of the wheels against the road, yeah? Okay? Between the wheels and the road, okay? So that's the friction force, that's the distance. Okay, so let's suppose you skid 10 meters. 10 meters. Now we repeat. We go twice as fast. We get twice the momentum, yeah? We go twice as fast. We step on the brakes, we skid to a stop. We skid further. Some people say, well, twice as fast, you're going to skid twice as far. Tilt. Not twice as far. How much far? Check the neighbor. See if the neighbor knows already. Twice as fast, gang. How many say twice as far? How many say more than twice as far? How many can calculate it to be F-O-U-R? 4 times as much. So you're going to skid. If you got 4 times the energy, you're going to skid 4 times as far. It turns out the friction force won't change with speed. How much the tires in the road grab each other does not have to do with speed. See? So you get the same friction. Now the same friction is going to drag you 4 times as far. That's why people going a little bit, when you first learn to drive, you've got to pick this up savvy-wise. You know, you go a little bit faster, you stim on the brakes, and it's surprising at first that, wow, it took so much longer to stop. Or you boost that car up to 3 times as fast now. 3 times the speed, okay? So not 30, not 60, but 90 kilometers per hour. Now with 3 times the speed, you know you got more energy, more kinetic energy. Some people know how much more. Check with a neighbor. How many say 9 times as much energy? E. That means you're going to skid how much further? 9 times as far. That's right. You get the idea? So kinetic energy is velocity dependent squared. Here's a little device that's kind of nice. It's a portion of a racquetball, and I can invert it. When I do that, am I giving it a little energy? I'm going to drop this and watch. Did you see that? It bounced higher than when I dropped it. HC. And here's another question, too. Will it always bounce higher from where I drop it? If I got higher up, would it still bounce higher? Where is the point where it will not bounce higher anymore, and why? Think about that. Show you another idea with energy. Here's a super ball. The super ball, I'm going to let it go. Some people think a super ball will come up to the same height, but it won't. It comes up to about a little bit more than half height. Okay? This super ball is guaranteed to give 1,000 bounces. We got this morning. Troy's been playing with it. Troy, how many bounces did you get on it? 995. 995. Okay, there's 96, 97, 98. Okay, let's see. 999. 1,000. Sure enough, that's true. Let's try it again. 1,000. Its elasticity is gone, gang. Think about that. Catch you later. Physics. Woo!